In a previous video, we examined a simple resistor capacitor circuit. Now let's do the same for a simple resistor inductor circuit. Recall that in a resistor capacitor circuit, if you take the resistance and you multiply it times the capacitance, you get time. You get something that we call the time constant. In the resistor inductor circuit, the time constant is L divided by R. In a previous video, we presented the equation for the output voltage if we give a sharp voltage at the input, VI. And we determined that the output voltage was VI times 1 minus e raised to the minus t divided by the time constant. If we do the same for the RL circuit, we get an equation that is a little similar. We get V out is equal to the V in applied at the resistor input times e to the minus t power divided by the time constant, which in this case is L divided by R. So we get an equation that's a little similar. For example, if we take this 1 minus and we remove it and we replace RC by L divided by R, we get the equation on the right for the RL circuit. So let's examine what's happening in the circuit when we give it an input voltage that starts at 0 volts and it goes to some higher voltage that we'll call VI or V input voltage. Now we know an inductor resists change in current. So as we apply this voltage, a current is going to want to flow through this resistor, through the inductor to ground. And the inductor is going to prevent that from happening. So at the initial time, when we initially transfer from 0 to VI at the input, we're going to have no current flowing in this circuit. And because we have no current, for example, flowing in this resistor, the voltage drop is 0 across the resistor. So that means initially all of the voltage at VI is across the inductor. So let's examine that in more detail. If we plot the output voltage VO versus time, something like this. As the input changes, we get a full drop across the inductor, and as time proceeds, this voltage comes down and approaches 0 volts. So this is our time axis, this is our voltage axis, and this is our V out. So we know that the inductor will resist change in current. So if we plot current down here, we know that initially when we apply this input, that the current is 0, and the current will build up over time and reach a maximum and then remain flat. So let's examine what's happening. We presented previously that this current, I, is related to the area of the voltage curve. For example, if we take a unit of time out here and we calculate this area, that at this point in time, that the current change is proportional to this area change. Now if we take another unit of time, say out here, and we calculate this area. Now notice that this area is less than the previous area. So the corresponding change in current is less. If we do the same thing again, we take another unit in time, we compute this area, the current change is proportional to that area. So for this time, the change in current has decreased because this area has decreased. So the area keeps decreasing, and the rate of current change decreases also. So this current is changing slower and slower as we get up to the top here. At this final time out here, all of the voltage is across the resistor and no voltage is across the inductor. Now let's take the same inductor resistor circuit and solve a problem. Let's draw the output voltage for that rapid changing input. We know that the output voltage is going to fall over time and eventually approach 0 volts. So if their input started at 0 volts and it changed by the amount VI, we'll start at this voltage and the curve will fall down. And let's examine the region where this curve is approaching 0 volts at some later time. Let's take a unit of time, and let's mark it here. And let's take a second unit. It'll be approximately a time constant. We'll take another time constant and another time constant. So this time here is L divided by R. So here we have 1, 2, 3, 4. Let's take another time constant, 5. At this point right here, we are at 5 time constants of time. And let's compute the voltage V out at 5 time constants after we apply this input voltage VI. So put your video on pause and see if you can solve that problem, and then come back and I'll present the solution. So let's use our formula to solve this problem. V out is equal to the applied input voltage times E raised to the power minus T over the time constant, which is L over R. Now we want to compute this equation where T is equal to 5 time constants, or 5 times L over R. So if we substitute T, we'll get VI times E raised to the minus 5 L over R divided by L over R. And our L over R's will cancel, and we're left with VI E to the minus 5th power. So we can rewrite that as equal to VI divided by E to the plus 5 power. And we can solve that. We know that, that's right, VI. We know that E is equal to 2.71828, and that's raised to the 5th power. So if we do that calculation, we get VI divided by 148.4. So at 5 time constants, our V out is equal to our input voltage VI times 0.0067. So we are almost at 0 volts. We're not quite there. If this were a 1, then we would be within 1%. So since this is smaller than this being a 1, we're within less than 1% of the final value at 5 time constants.